Hey everyone, welcome to The Explainer. Have you ever caught yourself wondering exactly how apps like Netflix, Twitter, or Discord manage to load massive, mind-boggling amounts of data almost instantly? I mean, millions of people are clicking, scrolling, and streaming all at the exact same second, yet everything just magically works without buffering? Well, there's no magic involved. Today, we're decoding the hidden architecture of speed that makes the modern internet possible. Okay, let's dive into this roadmap. First, we'll look at the need for speed, then exactly how caching works, before we officially meet Redis. After that, we'll cover the strategies and challenges, and finally wrap up with how all this powers the modern web. All right, kicking things off with Section 1, the need for speed. Now, what's really interesting about this slide is the sheer difference in physical bottlenecks. We all know how annoying a slow website is, right? Well, your CPU cache is operating in literal nanoseconds. RAM? Also incredibly fast. But the second you drop down to solid-state drives, hard drives, and way down to a network database, the speed just falls off a cliff. So if a hugely popular app tries pulling every single piece of user data from that bottom-tier network database, the whole system is just going to overload. We literally can't rely on those standard databases for every single request. Think of it kind of like a giant university library. Without caching, it's like a librarian running down to the dusty basement archive every single time a student wants a book. If thousands of students show up at once, yeah, that librarian is completely overwhelmed and the line goes out the door. But with caching, the librarian keeps the most popular, frequently requested books right there on the front desk. Boom. Students get what they need instantly, and the workload drops massively. Moving right along to Section 2, how caching works. So, bringing that library analogy into the software world, a cache is just temporary, high-speed storage. It holds copies of the stuff people ask for most often, serving it up instantly and taking the heat off the main database. Just remember, this high-speed layer is exactly like our librarian's front desk. It's not the permanent home for everything, but it's where the absolute most important data lives right now. So, what does this look like when everything works perfectly? We call this a cache hit. Step 1, a user logs in and asks for their profile. Step 2, the system checks the cache first. Step 3, the data is already sitting right there. It gets returned immediately. I mean, we're talking microseconds here. The user feels absolutely zero lag, and honestly, that slow database down in the basement doesn't even know the request happened. But, what if the data isn't there? Well, that's a cache mess. Step 1, the system checks the cache but comes up empty. So step 2, it actually has to query that slow database. In step 3, once it finally gets the data, it makes a copy and throws it into the cache. Finally, step 4, it gives the user their response. So yeah, that very first request, a bit sluggish because of the basement trip, but by storing it during step 3, it paves the way for every single future request for that data to be lightning fast. Which brings us to Section 3, Meet Redis. Time to introduce the real hero of our explainer. Redis is pretty much the industry standard. It's one of the most popular in-memory databases and caching systems out there. So the crucial point is that Redis stores its data directly in RAM instead of a typical disk drive. That's its ultimate superpower, literally. By living entirely in the system's memory, it completely bypasses those physical speed limits of spinning hard drives or standard solid-state drives. Let's rapidly fire through exactly why Redis is so wildly fast. First off, RAM access is almost instantaneous. Second, most operations run at O1 complexity, which basically means no matter how massive your data gets, finding a specific item takes the exact same tiny fraction of a second. Third, it dodges slow disk reads entirely. And fourth, it uses a single-threaded design. Think of it like a kitchen with one unbelievably fast master chef who never bumps into anyone else. It is ruthlessly efficient. But Redis isn't just some dumb storage locker. It's actually incredibly smart about how it organizes data. You've got strings for simple key-value pairs, list for things like message queues, sets for tracking unique data, like daily visitors, and hashes for storing user objects. Oh, and my personal favorite, sorted sets. These automatically order items by a score, which makes them absolutely perfect for things like real-time gaming leaderboards. All right, let's pivot a bit. Section 4, strategies and challenges. Because look, with all that blistering speed comes some serious engineering challenges. You can't just dump all your data into RAM and expect it to work flawlessly forever. Let's move to the cache aside strategy, often called lazy loading, and see how this builds on what we talked about earlier. The app checks the cache, and if the data is missing, it grabs it from the main database and then saves it in the cache for next time. It's essentially that cache miss flow we just went over. Super common, but it does mean that first user always takes a slight performance hit. But what about when data needs to be updated? This is where we hit a constant engineering trade-off between speed and safety. With a write-through cache, data is written to the cache and the main database at the exact same time. It's awesome because everything is perfectly in sync, but doing two things at once slows down the write process. On the flip side, a write-back cache writes data only to the high-speed cache first, updating that slow database way later. Extremely fast, right? But if that cache server crashes before saving the data to the basement, poof, that data is gone forever. Then you have the nightmare of stale data. Imagine you're online shopping. You click on a cool jacket for $50, hit checkout, and suddenly realize the database bumped the price up to $100 an hour ago? Yeah, that's a fast way to lose a customer. To fix this, engineers use TTL, or time to live. You basically stick a ticking timer on the cache data. Once time's up, the cache automatically nukes it, forcing the system to go fetch the fresh, accurate info from the main database next time. And we have to remember, while RAM is ridiculously fast, it is also highly limited and really expensive. You will eventually run out of room. So when that front desk gets full, how does the librarian decide which books go back to the basement? Those are your eviction policies. The system might toss out the least recently used item or the least frequently used. Sometimes it's just first in, first out, or honestly, sometimes it just kicks things out completely at random. You just have to set the rules based on whatever your specific app needs to do. Quick side note here, because I want to clear up a really common misconception. People mix up CDNs and application caches all the time. A CDN, a content delivery network, uses global edge servers to store static stuff. Think images, videos, your site's layout files, and it puts them physically closer to the user. But an in-memory cache like Redis, that's storing dynamic, changing app data, like your active login session or a live chat. They both make the web incredibly fast, but they solve two completely different bottlenecks. Which leads us to our final stop, Section 5, powering the modern web. Let's zoom out a bit and look at the real-world scale here. And this brilliantly illustrates just how vital this is. We're talking about heavyweights like Netflix, X, GitHub, Uber, and Discord. These aren't just your standard blogs, right? They fundamentally rely on Redis and in-memory caching just to survive those massive, totally unpredictable spikes in global traffic every single minute of the day. This invisible architecture is literally powering your everyday life. When you open a streaming app and you're already logged in, that session is almost definitely sitting in a cache. When a site blocks a bot from spamming refresh, that's API rate limiting, pinging a lightning-fast memory store. Your real-time rank in that game you're playing, sorted sets in Redis. Heck, even modern AI chatbots use it to instantly remember the context of your conversation without having to sluggishly read a hard drive. So we've seen how keeping data right at the surface, right at the librarian's desk in RAM, is the absolute secret sauce behind the instant responsive web we all expect today. But I want to leave you with something to think about. As the world goes all in on real-time analytics, 24/7 streaming, and incredibly complex AI, our data is just exploding exponentially. If systems like Redis rely on the physical limits of expensive RAM to stay fast, what happens when our massive global data outgrows those limits altogether? How will the architects of tomorrow keep the internet running at the speed of thought? Thanks so much for joining me on this explainer. Keep asking those big questions, and I'll catch you on the next